Okay, in this video, we're going to look at hypothesis testing with the normal distribution. So now we've reviewed the normal distribution and how to use your table. But if we have an x being a normal distribution with mean mu and variance sigma squared or standard deviation sigma, then x bar, okay, and that stands for the mean, but it's actually the distribution of the means of sample size n is normal. So if we have a normal distribution, then the distribution of the means that we would get from samples of size n is also normal. And so that's what this represents here. And that's going to have mean mu. Notice that's the same, so the same mean. But what's going to happen here is we're going to use sigma squared over n for the variance, okay? And again, remember this is variance, and you have to know the difference of when we use variance and when we use standard deviation. And standard deviation would be the square root of this. N is just my sample size. So if this is the variance, then my standard deviation would be the square root of this whole thing. So I could write that as the square root of sigma squared over n, which actually simplifies to sigma over the square root of n. So you might see this used this way or this way, but just make sure you know the difference. Now, there's two ways that we can do hypothesis testing, and you do need to know both of them, but if not asked for specific things, like a critical value or a critical ratio, or you'll see as we go through this that sometimes one is better than the other. But if you're not asked for a specific thing, then you can choose your method, but you do need to know both, okay? So for a critical value, what we're going to do is we're going to take the mean mu, and we're going to add or subtract, and that's based on our hypothesis test and which way we're testing, so I'll show you that. We're going to add or subtract k times, notice that this is the same as this over here. So this is the standard deviation, which is the square root of variance. So you just have to make sure you have the right formula. Okay, and k is coming from our table. So k is basically our z value from our normal table. Okay, so that's the, you'll see this. I'm going to do both of these. So this is critical value. Now, critical ratio, we find the z value that we're going to use by taking the observed mean. So lowercase x with a bar over it is the observed mean. So our mean of our sample minus the expected mean, the mean that we were given, which is mu, over just standard deviation. So this actually shouldn't say sigma. I think your notes are correct, but this should say standard deviation on the bottom. Okay, so those are the two formulas that we are going to be using. So now let's look at this. Okay, so in this example, Amma Williams believes that the carbon dioxide level in Sydney has risen above the usual level, so the usual level of 328 parts per million. A sample of 10 specimens of Sydney air is collected and the carbon dioxide level within the specimens is determined. The results are as follows. So here you have the values, the data that was collected, and you know how to find the sample mean. That's something we've done for a while. We did that last year as well. The sample mean, I'm just going to add all these up and divide by 10 since there are 10 specimens. And when you do that, you get 331. Okay. Extensive previous research has shown that the standard deviations of the levels, so they're giving you standard deviation of the levels within such samples is 2.5, and that the distribution may be assumed to be normal. So that's important to know that we're working with a normal distribution. And now we're going to use the data to test at 0.1% significance level Amma's belief that the level of carbon dioxide is above normal. So a lot of information there. The first thing we're going to do is identify our distribution. X would be normal. We would have 328 as our mean in this case, and we're going to have the 2.5 is the standard deviation, but remember what goes here is variance. So it'd be 2.5 squared over the sample size of 10. And then this is for the means here. Okay, so the means, the sample distribution of the means of the sample sizes would look like this. Okay, now We know we have a 0.1% significance, so that's going to be important in a second. Let's go ahead and identify our null and our alternative hypothesis. So the null would just be that mu is equal to 328 because that's what's expected, okay? That's the usual level. Our alternative hypothesis is that the mean mu is greater than 328 because she believes that it is above normal, okay? So now I'm going to show you two different things using critical values, because that was one of our formulas. So I'm going to do it using critical values. Okay, and then I'm going to do it using the critical ratio. So here's what I want you to see. If I think about, let's see, if I think about my normal distribution right here, okay, and this is greater than, so this is a one-tailed test, and we're testing to see if the mean is above 328. And my significance level is 0.1%, which is 0.001. What we're saying is that we would have an area of this normal distribution. Since it's greater than, we would be going this way, and this would be 0.001. But remember that our normal distribution reads less than. So if this is 0.001, then this is 1 minus 0.001, which actually equals 0.999. So I'm trying to find the value of this, the z value of this value, which makes this 0.999 because it would also make this upper part 0.001. And what we found here is p, our probability, okay? And so this is a little bit different than normal where you have a z value and you find the probability. In this case, we have the probability of this area here, which would be 0.999, and we want to find the z value. So what I would normally do is I would find this value in the middle of my normal distribution table that you have, and I would find the corresponding z value. But what's really nice, if you look at your reference sheet, is at the very bottom, there's a little small table that has p-values, probability values, and z-values. And so if you find the 0.999 at p, then it's going to tell you that the z-value is 3.090. And in our critical ratio, we also use this as k. Okay, so that's where I'm getting this value. Find your reference sheet, pause the video, find your reference sheet, and look at the very bottom, the table there. So I have this value. So now what we're going to do is we're going to use this formula. We're going to do the expected mean, okay, or our normal mean, our mu, plus, because it's greater than, because I'm going right, plus this k value, 3.090. And then I want to multiply that by the square root of this. And so however you want to write that, you can just write the square root of this, or you can write 2.5 over the square root of 10, because that's how it simplifies. When I do this, I get 330.4. Now, because we were testing greater than, what this is telling me, my critical value is really telling me my rejection region, or my critical region. So my rejection region is when the mean, the sample mean, is greater than, because of this 330.4 that we found. So if my sample mean is greater than 330.4, we would reject the null. And so our sample mean was 331. So 331 is indeed greater than 330.4. So we would reject the null and say that there is evidence at 0.1% significance level that the carbon dioxide level is above normal. Okay, so that's how we do it with critical values. Now we're going to do it with critical ratios. Okay, to do critical ratios, I'm going to find my z value by taking my sample mean and subtracting my expected mean, which was mu, which was 328. Divided by, again, it's going to be standard deviation, which is the square root of variance here. So you can write it as the square root of the whole thing if that is easier for you to remember. When I square root this, I get 2.5 over the square root of 10. So however you want to write that. This gives me 3.79. So what I'm doing is I'm actually comparing this number to this z value. And if this value here is greater than that, since this is the area I'm looking for, if this 3.79 is greater than that, then it's in my rejection region, because that's what this red part is here. This is my rejection region. Okay, so I can say here that 3.79 is greater than 3.090, and so I would reject the null and I would make a statement about that. Because this 3.79 is in this region right here. Okay, that's my rejection region. Okay, and so that's how you do critical values and critical ratio. So we're going to look at another example. Okay, a manufacturer claims that its light bulbs have a lifetime which is normally distributed with mean 1,500 hours and standard deviation 30 hours. A shopkeeper suspects that the bulbs do not last as long as is claimed because he has had a number of complaints from customers. He tests a random sample of 6 bulbs and finds that their lifetimes are 1472, 1486, 1401, 1350, 1511, and 1591. You get the idea here. This is our sample data. Is there evidence at 1% significance level that the bulbs last a shorter time than the manufacturer claims? So what we're going to say is our mean, our sample means, or our distribution sample of the means, is normally distributed with a mean of 1,500 hours. And they gave me standard deviation here, so I'm going to write 30 squared over n, which was 6. That's what goes there. Then we're going to state our null hypothesis, which is just that mu is 1,500. And we're going to state our alternative hypothesis, which is that in this case, mu is less than 1,500 because we're trying to test to see if there's a shorter time. Okay, I do need to find the mean of my sample. So my sample mean here, when you add all those up and divide by 6, you get 1,468.5 as my sample mean. Again, I'm doing 1% significance here. So what we first want to do is we want to look at our normal distribution, and I encourage you to draw this each time. So I'm testing less than now, okay, and a 1% significance. So I have some area over here, and this should be 0.01 because that's what 1% is written as a decimal. And so what I want to do is I really just want to find that z value that goes this way, that makes this less than 0.01. But what happens here is, unfortunately, because this is our middle here, this is going to be a negative value, and that's not in your table. So what you need to do is you need to think of the symmetry of it, okay? This over here must then be 1 minus 0.01, which is going to be 0.99. So P is 0.99. And that works because if I had this area over here, this area would be the same. So it's just the symmetry, even though this is what I'm trying to find. Okay, so all I need to do is take this 0.01 and subtract it from 1, and I get 0.99. And then I want to find this in my normal table, but I actually want to look at that table, that small table at the bottom of my reference sheet that says P equals 0.99. And so Z, if P equals 0.99, Z equals 2.326. Only you have to understand that since we're not looking at this one, we're not here, which is what it would be if we had greater than here. We are looking at this, so Z is going to be negative because you can clearly see that it's on the negative side. So negative 0.326. That's the one we're going to use. But we're just using symmetry to figure that out. So now, what we're going to do is we're going to use critical ratio in this case. And again, it's preference. Z would be my sample mean, which is going to be 1468.5 minus my expected mean, which is always this, divided by the square root of this. So I could just write it as the square root of 30 squared over 6 if that's easier for you. And when you do that, you get negative 2.57. And remember, for critical ratio, all I want to do is see if this is in my rejection region, which is this right here. So if this Z value, this here, is negative 2.326, is this one to the left of it inside that region. And negative 2.57 is less than negative 2.326, which means it's in my rejection region. So we would choose to reject the null hypothesis, and we would say that there is a evidence at 1% that there's a shorter time for the bulbs. Now, what if we do critical values? Well, for critical values, what we do is we take our mu, mean, and you have these formulas, you just need to memorize them. And since we're going less than, we want to subtract because we want to go to the left. We're going to still use this value here, but we're going to use the positive version of it because I'm already subtracting. So when we have found this Z here, we're still using the same Z value, okay, versus comparing it here. And then I have the square root of 30 squared over 6. So I want to do that math. When I do that math, I get 1471.51. So what this means, and if you were ever to find the rejection region, you would have to do it this way, which is why you need to know how to do critical values. Because if they said find the rejection region, this is it. You have to do it this way. But our rejection region, since we're going less than, is if the sample mean is less than 1,471 and 51, then I would reject the null. And so now we got to check our sample mean. This was our sample mean. Our sample mean was less than 1,471.51, and so we reject the null. So either way, our conclusion comes out the same, but you have to know the difference. So this one's nice, but this one you have to know if you were asked to find the rejection region, because that's what this is, okay? Or the critical value, that's this one. So just be really careful and make sure you know those. Okay, we're going to look at this one, and we have several questions for this one. So observations over a long period of time have shown that the mass of adult males of a type of bat is normally distributed with mean 110 grams and standard deviation 10. So probably the first thing I'm going to write is that I have a means are normally distributed with 110 as my mean, and then in this case the standard deviation is 10, so I'm going to have 10 squared over however many are in my sample size. And so a scientist has a theory that in one area these bats are becoming smaller, possibly as an adaptation to changes in their environment, and he plans to trap 20. So that's what goes on the bottom here. Weigh them and then release them. He will then use the data to carry out a suitable hypothesis test at the 5% significance level. So part 1, state the null and alternative hypothesis. I want you to pause the video for just a minute, state those, and then check your answer with me. Okay, so our null hypothesis should just be that mu is 110, and our alternative hypothesis should be that mu, in this case, is less than 110 because he thinks the bats are becoming smaller. Okay, in this case, we are asked specifically for the critical value for this test, which means you have to use that method. So take a minute, find the critical value, or in this case, the value is the number, but then the rejection region, and check your answer with me. Okay, so what we're going to do is we're going to draw our normal distribution. This one's less than, and we have a 5% significance level, so I'm looking at some region down here that would be 0.05. What that means is that this region is 1 minus 0.05, which is going to give me 0.95. So I'm going to find that on my table, and with that, I'm going to get that z is going to be 1.645. That's the z value I'm going to use. Up here, it would be positive. Here, it would be negative if we weren't using this method, but we are. So we're going to do 110 minus 1.645, and that's really why we can use the positive, because we're subtracting anyway, so we're going to the left, times the square root of this right here, which is 10 squared over 20. When you do this, you get 106.32. That is my critical value, and we should state that to 3 significant figures if that's our final answer, but my critical value is 106, okay? So what we do know from that, even though this is not what you were asked, you need to understand that if you were asked the rejection region, you would say when the mean, the sample mean is, in this case, we're going less than, so when the sample mean is less than 106, that would be your rejection region. If they ask you for the critical value, it's just this, okay? All right, so part 3 says find the probability of a type 1 error. I want you to think about that for a second and try to answer this, and then check your answer with me. Okay, think about what a type 1 error is, guys. A type 1 error is wrongly rejecting the null. And at a 5% significance level, which is what gets us this z value and this critical value, a type 1 error is just 5%. It is the same as the significance level, which we learned when we did the binomial distribution, okay? All right. If, in fact, the mean mass of bats has reduced to 108 grams, but the standard deviation remained unaltered, calculate the probability that the test will produce a type 2 error. Okay, so here's what I want you to think about on this one. What we know so far is that if the sample mean is less than 106, then it's in the rejection region. That's what we learned previously, okay? We found the critical value and we found the rejection region. If that's true, then a type 2 error occurs if the mean is greater than 106. So what we actually want to do this problem is we want to just find the probability that z, or that x in this case, we'll say the probability that the mean is greater than 106. And this goes back to what we reviewed for the normal distribution. We want to standardize this, so we want to find the probability that z is greater than, and we're going to do the 106.32. We're going to use the whole value minus 108 over, and 108 comes from this. That's our actual mean now, the mean that we know to be true, divided by, again, the standard deviation, which, remember, I know I'm running out of room here, was 10 squared over 20. Okay, so when we do that, we get the probability that z is greater than negative 0.751, which from your table, this is just like what we reviewed. From your table, we say, well, that's greater than and that's negative. So ultimately, they cancel each other out, and I get phi of the positive 0.751. And then you go find that on the outside of your table, and the inside value is 0.7737. So that's 0.774. That's the probability of a type 2 error given my new value. Okay, that's the thought process you have to go through. So now, then we're told the mean mass of the scientist's sample of bats is actually 107 grams. Once he did this sample, this is what he got. So carry out the hypothesis test and state what type of error. In this case, we've already found the rejection region. Remember, the rejection region was when the mean was less than 106. So if he found that the mean is 107, 107 is not in the rejection region. And so we fail to reject the null. And we would state there is no evidence to support the scientist's theory at the significance level that we were asked, which was 5%. Now, it does say what type of error, if any, occurred. If we fail to reject the null, guys, the only error that could possibly be is type 2. Because a type 2 error occurs when we fail to reject the null, but we should have. So if there was an error, it was a type 2 error, okay? And then really part 4, because we found this probability, which is a high probability, it shows that a type 2 error is probably likely, but the type 2 error would be the only thing that could have occurred. Okay, we're going to do one more of these. So in the past, a machine has produced rope which has a breaking load which is normally distributed with mean 1000 N and standard deviation 21. Okay, a new process has been introduced in order to test whether the mean breaking load has changed. It doesn't say gotten or increased or decreased. It says changed. A sample of 50 pieces of rope is taken. Excuse the grammar, should be taken. The breaking strain of each piece measured and the mean calculated. A says define a suitable null and alternative hypothesis for testing whether the breaking load has changed. Now, I still think you should state this distribution of the means as our mean is 1000 and our standard deviation is 21. So I'm going to write 21 squared over 50 for my standard deviation there. Okay, but it does just ask for a null and alternative. So take a minute, write your null and alternative hypothesis, and then check your answer with me. Okay, my null hypothesis is that mu is equal to 1000 because that was the mean I was given. And my alternative hypothesis is that mu was, in this case, not equal to 1000 because it's a two-tailed test. Okay, so we're going to talk about that. Now, taking the sample, so we're on part B, taking the sample mean as the test statistic, find the rejection region for the sample means for a hypothesis test at 5% significance level. So if we have, let's do part B, if we have 5% significance, but it's a two-tailed test, then remember I have to do 5% divided by 2, which gives me 2.5%. So I have to account for that. So if I'm looking at my normal distribution now, what I'm saying is there's 2.5% this way and there's 2.5% that way. So this is 0.025 and this is really 0.025. But, sorry, 0.0 0.025. There we go. So what I want to do though is I need to find this z value and this z value. Now this one, they're going to be the same, but this one's going to be positive and this is going to be negative. And since my table reads less than, what I want to do is I really want to say, what is this value over here? Well, that's just 1 minus 0.025. And when I do that, I get 0.975. Okay, so then I want to go find, this is my p-value, 0.975, and I want to go find my z-value on my table, and so that's at the bottom, and when you do that, you get negative 1.960. So this is the negative version, and this is the positive version. So really, I'm going to state both. I don't know why I wrote that one as negative. You actually get the positive when you look at your table, but it could be either based on the direction that we're going. So now what I'm going to do with this, since we're going to do a rejection region, we have to say I want to do 1,000, which is our mean, and I want to add this z-value, 1.960, times my standard deviation, which is the square root of 21 squared over 50. Okay, but I'm also going to do the other direction. I'm going to do 1,000 minus 1.960 times this. And when I do these, this one's going to give me 994.179, and this one's going to give me 1,005.82. Okay, so what this means is that my rejection region occurs if the sample means are less than 994 to 3 significant figures and greater than, in this case, 1,006. And actually, that's not to 3 significant figures, but that's what I would be testing for that. So this is my rejection region, because we got to consider this way or this way, where this red colored in here is. Okay, so on part C, it then says the sample mean for the 50 pieces of rope was 1,003. What can we deduce? Well, 1,000, let's rewrite that. 1,003 is not in the rejection region. It's not less than 994, and it's not greater than 1,006. So it's not in the rejection region. So we fail to reject, can't write today, sorry guys. We fail to reject the null hypothesis, and then we make a statement based on our context. Okay? All right, review what you need to, but understand this and understand how to use these formulas, and I will see you in class.